Okay, we've moved our input to the channel 2 or channel B input, and we're going to run the same test as quickly as we can that we just ran on channel 1. We want to make sure that both channels are functional, right? Right now we are at 20 hertz, and we are on the 0.01 volt per division scale. We are at 5 milliseconds per division input, time base wise. So 5 milliseconds times 10 would be 50 milliseconds, which would be 20 hertz. So we are displaying one cycle of a 20 hertz wave on the screen. Alright, so let's take us to 2 milliseconds per division and give ourselves one full cycle. And that would mean that at 2 we would need a 50 hertz signal, and right now we are reading a 50 hertz signal, and we need to go up. There we go. Now our reference scope is matching. Okay, so we have a 50 hertz cycle being displayed at the 2 millisecond per division time base setting, and it matches on both screens. Alright, we are going to go to 1 millisecond per division, and we adjust for one full cycle. And that would be 100 hertz that are required at 1 millisecond in 10 divisions. And there we have 100 cycles being displayed on the counter, and we have this similar reference signal. Okay. 0.5 milliseconds. At 0.5 milliseconds per division, 10 divisions, we would need 200 cycles per second to give us one cycle on the screen, and we are 198, essentially 200. We could touch that up, it would make a difference on the screen. And that indeed will match our reference. There we go. Okay, so we advance to 0.2 milliseconds per division, and we kick ourselves up on the generator and adjust for one cycle. 0.2 milliseconds per division, 10 divisions, 2 milliseconds, that'd be 500 cycles, so that's a 497, 500 cycles. So we're good. We still are displaying full 0.4 volts peak. Go to the next range and adjust for one full cycle. Just about there. That's one full cycle at 0.1 milliseconds times 10 would be 1 millisecond. That's 1,000 hertz. 998, close enough. And putting our reference on the same screen, we are at 1,000 hertz with the same signal. Alright, now we are at 50 microseconds per division. And 50 microseconds times 10 would be 500 microseconds, which would be 2 kilohertz, and we are running 1.996, so 2 kilohertz. And our display is the display of the reference scope. Alright, let's okay, at 20 milliseconds, 20 microseconds per division times 10, that'd be 200 microseconds, and we'd be at 5 kilohertz, and we are reading 5.08, and there we go. Now we have the reference still looking just like our test instrument here. Drop again to 10 microseconds per division. 10 microseconds per division, 10 divisions, that'd be 100 microseconds, which would put us at 10 kilohertz. 10 times 100, yeah. And then our reference is displaying the same. No shift in output vertically, no shift in output vertically, so we're still fine. Go ahead and reduce ourselves again, 5 microseconds per division. So times 10 would be 50 microseconds across the screen, and that would be 20 kilohertz. Reference. Okay. Go ahead and take her down 2 microseconds per division. Adjust our generator. 2 microseconds per division, 10 divisions, 20 microseconds. That'd be 50 kilohertz, and I'm running 49.8. We can touch that up a bit. Alright, there's 50. Didn't make any change really to the screen, and it matches our reference. Okay, 1 microsecond per division. So at 1 microsecond per division, that's 10 microseconds across the screen, which means that have to be 100 kilohertz to show that one cycle, and we are running at 100.77, which close enough, huh? And then finally, our last scale, 0.5 microseconds per division. We adjust for 1 full cycle. We gotta be close right about there. That should be 200 kilohertz, and we are running, I'm showing 205. Go ahead and we'll adjust her down. Alright, 200 kilohertz, and no appreciable difference. 1 cycle on the screen, and essentially 1 cycle here too. Let's move the 0 a little bit. Okay. And we still are reading the full scale vertical 0.4, so we haven't begun to see any losses due to frequency yet. Okay, now we can't go any higher on our range, so that now we have to start displaying more cycles on the screen. Let's go ahead and we are right now going to display 1 megahertz. Okay, that's about 1 megahertz right there. Yeah, it's 1,000 kilocycles, so 1 megahertz. And what we should see is that we have a cycle every 2 divisions. Yes, because that's 0.5 microseconds per division. So you have 1 microsecond in 2 divisions. So you have 1 cycle of 1 megahertz. So that's being displayed properly. We're just showing the same on the reference scope. Okay. Let's go ahead and kick ourselves up to 10 if we can. So we've achieved 10 megacycles, and we've started to drop a little bit in vertical, which we'd expect because we're beginning to hit the end of our range. It's a little bit hard to display here, but at 0.5 microseconds per division, it would be 1 microsecond in 2 divisions. And I think we would find that we have 10 of these in 2 divisions. 1 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes. Make it a little bit easier. We'll go times 5. Are going to take 10 divisions to do what 2 would have done. So we should get 10 of these in 10 divisions. So putting the 0 point here, here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 peaks and 10 divisions. That's what we want. All right, let's go ahead and kick this thing up to 15 megahertz. All right, 15 megacycles. Good. And at 15 megacycles, we have now dropped 1 full division from our 4 tenths that we had in peak, and we are now at 3 tenths. So we'll figure out that. Well, we did figure that out for channel A. That is the 3 dB point, actually a little bit better than. And we should be able to see 15 of these things being displayed in 10 divisions. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15. 15 megacycle trace. We're looking good. Okay, so we just did the math here on our calculator, and we find that with the output being 0.3 now, where we started out at 0.4 volts peak, then we are running 0.3 over 0.4, take the log of that, times 20, and we wind up at a negative 2.5, which is less deviation than the 3 dB point would be. So we actually have a little bit more frequency response available here than the rated, which is good. So you've got just a little cushion there. The scope seems to be functioning well and is very comparable to our reference scope over its frequency range.